I'm going to try to project my voice because Mateusz and myself are tag teaming on this. Firstly, good afternoon, and thank you for joining us for this presentation. Mateusz and myself, first we thought we were going to do it in 1 hour, but we found out we have only had 28 minutes. So this will go really fast, as we say at GPU speeds. A little bit of a little difference between the previous presentations, which I saw was on rule ensemble modeling. What we will be talking about is the role of GPU in accelerating the data science workflow. A lot about interactive visualization, data and analytical processing, and then machine learning as well. And I won't take too much time introducing ourselves beyond asking a question, which is, how many of you are familiar with MapD? Anyone's heard the company? Okay. A MapD employee and a couple of folks. It makes bear in mind to just give you a little brief introduction. But before we go into MapD itself, let's reintroduce GPUs for you. Or what is GPUs, which is general purpose GPUs for you. And so a typical CPU is something which has up to 32 cores, very powerful cores. Whereas the GPU has almost 3,900 cores, and that's getting more powerful over time. These cores are not it's not as powerful as CPU cores, but they allow parallel processing. So you can do things like filtering, aggregation, custom expression at really fast speeds. The second thing that GPUs are really good for is they have a very high memory throughput. They have almost 20x more memory throughput than CPUs do. So what you can see GPUs being used for increasingly is matrix multiplication, which is the core of machine learning. But we are also seeing usage, which is MapD is one of the company's pioneering usages for what we call dense linear algebra, fast Fourier transforms. All of these are basis of data and analytical processing. Talking about the company, will tell you a little bit about how we're making GPU-based data visualization and analytical processing happen. Is the first thing at the bottom of the stack is what we call core. It's a GPU engine which sits on top, it's a SQL engine that sits on top of GPUs. So like I said, it's using the GPU parallel processing to do a lot of analytical applications. And then there is Immerse, which is basically going to be the self-service front-end platform, which allows you to do interactive visualizations. So before we go into why and what, let me explain to you why, from a data science perspective, why this is important, right? Interactive visualization, visual analytics is the name of the game. So for a long time, there has been interactive visual analytics, which is reducing the impedance mismatch between the human cognition speed and the delivery of the data from the underlying software layers, which is data management, analytical processing, and visualization. Either you can only do it on small amounts of data, or you have to do it in a batch process with large amounts of data, which is you need responses at almost 200 millisecond speed, right? And to make this possible, it's been unlocked by the power of NVIDIA GPUs. That's one of the primary factors is making it happen, which is just the power of physics. There's a lot of IP and technological innovation happening on top of GPUs. The first one, as you can see, is the extreme speed. Is in addition to the parallelization of GPUs, is also what we call the LLVM compilation engine. I'll tell you a little bit about it. The other one is native rendering. So as you know, the GPUs, the reason they really emerged was for games and graphic processing. We take GPUs to do high cardinality rendering of information, and I'll show you that so you can understand what that really means. And finally, all this in a self-service interactive platform, right? That's one of the main reasons why you can use it as a business user without understanding the underlying platform below it. LLVM, I just talked about this. Let me quickly tell you what it is. It really stands for low-level virtual machine. So in a sense, SQL is a declarative language. It still has to be compiled into query plan. And this query plan tends to be having a large overhead because it prevents vectorization. Vectorization is really the parallelization of computation. So at MapD, our SQL is implemented using LLVMs. And LLVMs allow you to you're really able to squeeze at the level of handwritten queries. You can also target different architectures like x86, ARM, and GPUs, of course. And you can smartly move your data and the computation between the different layers of memory hierarchy, between the CPU, your GPU, and even your disk to some extent. That's the first factor where you're getting really a big turbocharge in your processing itself. Let's talk a little bit about the visualization layer. So most of the visualization is done on the front-end side using things like D3 and typical charting libraries like bars and histograms and pie chart. But what we talked about was the back-end GPU rendering, which is for a large number of, like millions of data points. You are able to use the server side to create a PNG, and it's composited on the front-end side. And this is really powerful when it comes to geospatial visualization, where you have a base layer. You're trying to show all the geo heat map of all the counties having certain dimensionality on it. And we're able to do it in sub-second speeds because we're able to take advantage of front-end and back-end GPU rendering. Well, don't believe me. There's a well-known blogger called Mark Litvinchik who's actually run some baseline, and you will see that the top 5 tend to be MapD in terms of performance. And these are typical architectures and hardware stacks which use your CPU databases from your Spark or Databricks machine to Vertica to a lot of other vendors. And this is not just a 1 or 2x. It's orders of magnitude much faster to use it. In fact, it's better to show it than to say it. Let me actually show you a quick demo of what you can do, right? So this is the, I guess I can't switch it, huh? Or is it a little slow to switch? All right. May need some help in demo. Yeah, we have to show a demo as well, so is that possible? Okay. Now I'll keep talking. So what Mark Litvinchik did was he used what's well known as the $1 billion taxi cab demo data, which is between 2007 and 2000 and the current date. All the taxi cab receipts, including not just taxis but also Ubers and Lyfts of the world, and his crunch demo on our browser. Is that it?
Can't you just? There you go. And where's which browser?
This is the browser here, but.
Okay. You need to go escape out of that. There you go.
All right. All right. I'll rewind. All right, so the data set is almost, if you see up here, it's almost 1 billion data points, records of information of taxi receipts, Uber receipts, spanning from the year 2009 to the current, not current date, but probably a year back. Now I'm going to show you some of the interactions. We've just created a very simple dashboard. And think of you as a data scientist who's looking at your data in a very descriptive way. And you go and drill in, and you zoom in, and say, you could say things like, what's happening in Times Square? I'll show only one demo because we'll run out of time. And you can see a lot of things happen. Firstly, you'll see that every chart which is associated with this was cross-filtered. This is what we call cross-filtering. Everything's updated in real time. Then you were able to see some interesting changes in information. You're able to see things like what is the heat map of all the pickup times, and you'll see it's predominantly going to be happening in the evenings or on the weekdays as comments to other places. And you can also see the, let's take one more. And then I'll be really quick about it. And you'll see the difference in meatpacking district, the difference at the speed of thought. You're able to find out that the heat map of where the pickup and drop-offs happens at 2 a.m. between 11 a.m. and 2 a.m., 11 p.m. and 2 a.m. on the weekends, which means it's predominantly a party place where people go out at night. You'll see the, it's mostly cash-oriented and credit, but if you go back in time, if you look at the most recent set of data, you'll see it's mostly credit card, so people are playing with credit card for the taxi rides. The point out here, which I was trying to make, is that the interactive speeds, which affords on 1 billion rows of data, is actually what is enabled by GPU, right? Let's just talk quickly about Go.ai. While GPU is helping you to really speed up your processing One of the big problems is that they live in silos. Different applications have to talk via the CPU when you have to do inter-process communication. So you have to go through the PCIe link, which is pretty slow, 4 to 10, 16 gigabytes a second. This is the world before we started the Go.ai initiative, which is early this year, which was a project started by both MapD, H2O.ai, and Anaconda. And we have other members join the consortium, which are members like Gunrock, Graph History, BlazingDB, and then implementation on TensorFlow and PyTorch. Basically, the idea is that we are having an intermediate layer so that you have only passing a pointer to your data set instead of passing the whole data back and forth. We use an arrow-like format called the GPU data frame so you don't have to serialize and deserialize information. And finally, you are actually doing inter-process communications for communicating between applications. What is the use of GDFs? It's used for interrogation of, first thing is interactive feature engineering to help you, like we saw, descriptive analysts ask you a question, find out what features are important to you, or maybe important to the model. The other ones we are seeing, which has come out from Volkswagen, is the interrogation of black box model. So you're able to really interrogate your model to understand and interpret your models. We'll talk a little bit down the line. And finally, enriching data of pre-built models. These are the three big application GPUs. I'm going to pass it on to Mateusz to talk about the GPU, H2O for GPU initiative. If you need this.
Okay. Yeah, my slides are not as pretty as Ashish's. I'm a software engineer, so sorry for that in advance. I started off at H2O as a Scala developer, and recently we moved on to GPUs. And the reason why is because, well, as Ashish mentioned, speed. So what we're trying to achieve is, does anyone know what scikit-learn is, the Python library? Yes, show of hands? No, not really? Okay, a few people. So scikit-learn is like that go-to library that people use for machine learning. The problem with it is it's purely CPU-based, and the developers don't really feel like doing GPU implementations because it's, well, not trivial. It's not only the computation model is completely different, also packaging the whole thing is, well, kind of painful. So we took it upon ourselves to actually implement as many algorithms as we can. So far we have an implementation of GLM, GBM, k-means. Recently we added truncated SVD and PCA. So if you guys feel that like you have some requests for algorithms that are really, really necessary, just give us a ping or visit our GitHub channel. We are trying to evaluate what to implement next. You probably have seen the demo Shri gave yesterday during the keynote. So that was our initial implementation. So one thing that people ask us is like, okay, why GPUs? And again, as Ashish mentioned, it's all because of latency and throughput, right? So CPUs are really good at latency, which means that if you have only a few tasks to perform, but all of those tasks are pretty computationally expensive and long, most probably CPUs will be better because they can do them faster. The thing with GPUs is that the cores are not as powerful, but there's just so many more of them that you can parallelize it much better. So if your task is highly parallelizable, GPUs most probably might be better. It also depends on the data size because, well, transfer from your RAM memory to your GPU RAM memory is not free. And this is what Ashish will be talking about later on, well, showing in the demo why we're trying to keep everything on the GPU and why we have this whole Go.ai initiative. So just to show an example why we want to use it in machine learning, like, again, as it was said, machine learning, well, bulk of it is just matrix multiplication. So if you have huge matrices and you will have an output matrix, that's just a series of multiplications and summations, sorry for that. So you will have thousands, hundreds of thousands, maybe even billions of those kind of operations, right? So each operation will be very small and very fast, but there's going to be a lot of them. So this is a perfect use case for GPUs. As you can see, this is our GLM implementation. Here we were training 4,000 models, both on CPU, using a double Xeon CPU, and several GPUs. So even with the one GPU case, we are still like 5-6 times faster. And as you can see, like both of those pieces of hardware, like they are very, very similar cost-wise. So there's really no reason to go to the GPU to the CPU. Same with GBM. If you want, Rory Mitchell, who's the main contributor to XGBoost, a very famous framework, is roaming around and will most probably be on the hands-on. You can poke his brains about this. As I mentioned, we have k-means. This slide is also a little bit outdated. We did a little bit of performance improvements, and like that's even faster. That's not only 30 seconds. It went down to around 15 seconds. So here we were doing 1,000 up to 1,000 iterations of the traditional Lloyd's algorithm on the home site data set. So the thing with TensorFlow and scikit-learn is that they don't have GPU implementations. So we had to run them with CPU. And as you see, like the difference is huge. And it gets bigger the more clusters you have. As I mentioned, we also have truncated SVD and PCA. And if you want, this is only like a very high-level overview of the whole framework because, well, we're running out of time. But after this session, there's going to be a hands-on in the afternoon with H2O for GPU. So if you guys are interested, you can just go there. And John McKinney, our director of research, will go through all our Jupyter notebooks and show how easy it is to actually get going. And also go more in depth in our implementations. Yeah, and then let's go to the demo. Ashish will show how we can actually stay on the GPU all the time.
Yeah, thanks, Mateusz. Like I said, I'm not a data scientist, so, and this demo is mostly art of possible. It's not a production beta or a production-ready product. But the first thing before we launch into the demo itself is I want to talk to you a little bit about how the products are used into your data science workflow. Many of you would understand this completely. So in terms of a data lifecycle or how a data science workflow happens, you have a data engineering side where data scientist is collating and enriching information from different sources. And the step after that is where the data scientist is looking at information from more data discovery perspective to understand features, features which may be revealed by some data-centric aspects, or the data scientist understands business and business metrics and can identify key features for it. It tends to be a very iterative process in the sense that you need a lot of descriptive analytics, and you need to understand data and drill down on data to understand what could be the ones that may be responsible for fitting into your objective function, to predict your objective function. And this is where you would use a MapD. MapD not only will give you that interactive speeds, but you can really look at large amounts of data. I showed you a demo with almost 1 billion rows of data. We have a shipping demo on our side, which has more than 11 billion rows of data. Large amounts of structured information. You can drill in interactively, have your hypothesis, and go to the next question. And then you would use, using the Go.ai initiative with GDF, you would punt it over to model scoring and model validation phases of it till you train your model, and you deploy it again using H2O.ai into a production landscape where you operationalize it and you're using it productively to make business decisions on your behalf. After this, where we are also seeing a lot of take-up on is model monitoring, and I'm looking specifically on black box model like machine learning models where this okay, explainability, let's use that word, is what you want to understand why a model is behaving the way it behaves. And this is where you would use by throwing a large amount of data to understand what is the output of the black box model, so you can understand and explain it. And sometimes there may be some regulatory needs where you are trying to show to an industry why the model is behaving the way it is. And this is where any MapD would, again, be very instrumental and useful. Let's go to the demo, and hopefully I'll be able to switch this time. This demo is a public data set called the Fannie Mae / Freddie Mac data set, where we have, as you can see, almost 1.1 billion rows of mortgage data for single family homes. All information from the origination, which is what is the information on the credit score of a person, the interest rate they got, the principal they're paying on it, and in addition to it, performance data, which are information about how the repayment happening, any changes in interest rates, and also delinquency, which is failure to pay the mortgage in time. What you're really trying to do, as you can understand, is what is a good predictor of delinquency or defaults. And like I said, after you're able to munch data and upload it onto a MapD system, you can interactively ask questions of it. Now, for instance, you could say, I'm only interested in those mortgages which have some aspect of distress on it. Anything which is more than 60 days of delinquency could be leading up to a default or distress. And you can quickly come down to the different attributes of it. I won't spend too much time because we are running out of it. But in a sense, what you're looking for is patterns in data which will show you whether it could be a feature which is worth investigating or putting in your model, or it's something you understand and you want to drill down into. So things like what's called loan-to-value ratios or spread at origination will be revealed in terms of either from a data-centric perspective, you look at it from some kind of variation, or it may not be indicative because it's pretty noisy information. Data scientists with a combination of both data science skills and business skills will be able to come up with the best metrics and features to select for the predictive models. Once you come up with this predictive analytics, you can go up to the machine learning tab, and you're able to really come down to selecting your features. So things like you look at a data set which you're using, and then you can select which are the algorithms you want to use. Right now, we've implemented 3 of H2O.ai's, including GLM, and linear regression and logistic regression. And then you come up with your objective function. In this case, it is to find out default delinquency, so delinquency status out here. And then let me just drop in some features into it just for the sake of showing it. Obviously, someone who is understanding the space will be a better judge of things. And this is where the handoff happens from MapD to H2O.ai. You're really seeing this GPU to GPU data frame, and you click on this, and the handover is happening. You can see the training is going on. And right now, I took a very small data set, so almost 35,000 rows only. And you saw a coefficient of determination of 0.233, which is really bad. So sorry, I'm not a data scientist. But what would happen is a data scientist will iteratively figure out what features. It's a very iterative process. You go back and forth, and you come up with what are the right features for this model, and you train it. And once you're done with the training, which maybe Mateusz, if you want to touch upon that, or okay, we can use that time for questions. And once you're done or you're happy with your model, then you can save it. The next step is you can use this model to actually predict, or you can use it to interrogate. You can interrogate this model by applying it to a newer data set. Let's just do a smaller data set and predict using that. So once you're done with this, you can go to a dashboard and see the actuals versus, you can look at the actuals versus predicted. So I'll see what is my delinquency status and just As you can see, it's really easy drag and drop. And I'm looking at what has been predicted. I'm just going to compare the two, right? So how good is the predictive power? And you can, now this have a very little data points, but I would usually create some kind of graph or some kind of scatter plot with it. There are different ways, obviously, to see the accuracy of models, which Mateusz can talk to more deliberately on it. But the MapD would be able to help you monitor and understand the performance of the model as well. With that, I think we kind of closed our main session. We rushed through it. We had to compress it from 1 hour to 30 minutes. But I'm hoping we were able to cover most of the aspects of the presentation. We can still ask questions. Okay, so sorry, I tried to do it because it's a different machine. Oh, perfect. Okay, that's perfect.
Okay, so
Yeah, go for it.
yeah, so for the first one, yeah, if you have a laptop with a GPU, then yeah, sure. Our only current requirement is that you're running a Linux machine. For now, we have Python wheels for Ubuntu systems. If you want to run it on CentOS or Red Hat, for now you have to build it yourself because we're working on an improved build system. But yeah, otherwise you just need an NVIDIA GPU with CUDA installed and you can run it without a problem. Yeah, there was a question about filtering. Well, we have at H2O a project internal which probably will go open source called data tables for Python. And most probably we'll try to implement GPU capabilities there for like sorting and joins. Sorting is pretty fast on the GPUs. So you can use radix sort and you can get some decent speed ups. It just depends like on the size of your data or whether the data is already on the GPU. If it is, then there's no overhead of sending it there. So you should see a speed up.
I think the second question, I can take that one.
Go for it.
Yeah, just add a little bit more meat behind what Mateusz shared in terms of GPUs for filtering and table joining operations. So GPUs are very well equipped to do data filtering and sorting, like Mateusz talked about the radix sort. Joining is a little more complicated animal, and this is what MapD has been solving, because when you look at joining on high cardinality sets on GPU, there's a lot of differences between the CPU, because you may have to do nested join versus a full inner and outer join. Feel free to check out MapD. We have an open source. The core database does this, and it's an open source product which people are using to take care of the operations. The thing about text fields is mostly tends to be variable length and not very well suited for GPUs. There are ways around it, but right now, a combination of fixed encoding, if you're able to encode text into categorical variables, categorical encoding, so that you can use it more performantly in GPUs. Otherwise, text is not really good for both CPU and GPU operations, nonetheless. Faster doing in text operations like filtering and substrings on CPUs, but we are actually doing it on GPUs right now for some of the subset of operations. And finally, I saw a question on how does MapD fit in a deep learning space. Like I said, we will help to accelerate the data science workflow. And in fact, deep learning is actually a very key area of innovation. Like I said, the Volkswagen Labs is using MapD for interrogation of black box models. So black box models being a machine learning model where you kind of know what the answer is, but you do not know why that was taken. So what Volkswagen is doing in that innovation lab is feeding a lot of information to the machine learning or the black box model to understand how it interprets that data, and then they're able to visualize it in MapD, because you're using a large data set. It's a highly dense data matrix which you're able to visualize and interactively interrogate. So that's probably also on the XAI side of things, not really deep learning for the sake of deep learning, which you would do predominantly on a H2O.ai product. I think we kind of,
Yeah, I think we're over time.
we are over time as well, so.
So yeah.
All right, well, thank you. Hope that was helpful to all.